An ideal operational amplifier, op-amp, is imagined as a perfect voltage-controlled voltage source. It obeys 3 key rules. Number 1, the input terminals draw zero current, infinite input resistance. Number 2, the output can drive any load without loss. Infinite open loop gain, infinite output resistance is 0. Number 3, the open loop gain a sub-OL is so large that even a microvolt difference between the inputs forces the output to swing to the supply rails. Because a sub-OL approaches infinity, the voltage difference between the plus and minus inputs in a closed loop circuit becomes essentially 0. This condition is called virtual short. The two nodes are at the same potential even though they are not physically connected. When the non-inverting input is tied to ground, the inverting node sits at ground potential 2. This is known as virtual ground. An everyday analogy is a very stiff spring that forces 2 points to stay at the same height. You can move 1 point, and the spring instantly pushes the other to the same height, even though there is no rigid rod linking them. Consider the classic inverting amplifier. The input resistor R sub in connects the signal source to the inverting input. The feedback resistor R sub F runs from the output back to the same inverting node, and the non-inverting input is grounded. Using the virtual ground idea, the inverting node is at 0 volts. The input current I sub in equals V sub in divided by R sub in flows into the node. Because the op-amp input draws no current, this same current must flow through R sub F, so I sub F equals I sub in. The voltage drop across R sub F is V sub F equals I sub F times R sub F, which equals V sub in divided by R sub in times R sub F. Since the far end of R sub F is the output, V out equals negative V sub F. The drop is opposite to the output direction. Therefore, V out equals negative R sub F divided by R sub in times V sub in, and the closed loop voltage gain is a sub V equals V out divided by V in, which equals negative R sub F divided by R sub in. The minus sign tells us the output is 180 degrees out of phase with the input. It is inverted. For example, if R sub F equals 100 kilo ohms and R sub in equals 10 kilo ohms, the gain is minus 10. A 0.2 volts input becomes minus 2 volts at the output. In the inverting configuration, the input impedance seen by the source is simply R sub in, because the virtual ground makes the node appear as a direct connection to ground. No current enters the op-amp, so the source sees only the resistor. The output impedance of an ideal op-amp is 0, but in the closed-loop circuit, the feedback resistor R sub F lowers the effective output impedance further. A practical way to view it, any change in V sub out forces a change in the feedback current which the op-amp instantly counters, making the output behave like a stiff voltage source. The Thevenin equivalent looking back into the output is roughly R sub out equals 1 over open loop gain a sub OL times beta, where beta equals R sub in divided by the sum of R sub in and R sub F, is the feedback factor. With a sub OL in the millions, this resistance is a few ohms or less. Thus, the inverting amplifier presents a low impedance source to the load, ideal for driving speakers, a DCS, or subsequent stages. The non-inverting amplifier connects the input signal directly to the plus terminal, while a voltage divider made of R sub G to ground and R sub F to the output feeds the minus terminal. Because of the virtual short, the voltage at the minus input equals the input voltage V sub in. V sub minus equals V sub out multiplied by RG over the sum of RG and RF. Setting V minus equals V plus equals V sub in yields. V sub in equals V sub out multiplied by RG over the sum of RG and RF. Rearrangings. V sub out equals V sub in multiplied by open parenthesis 1 plus RF over RG close parenthesis. Hence the closed loop voltage gain is a sub V equals 1 plus RF over RG. There is no sign inversion, the output follows the input polarity. For instance, with RF equals 90 kilo ohms and RG equals 10 kilo ohms, the gain is 1 plus 9 equals 10, so a 0.5 volt input becomes 5 volts at the output. The non-inverting amplifier sees the source directly, Therefore, its input impedance is the op-amp's own input resistance, which is effectively infinite, mega-ohms to giga-ohms. This makes the circuit very gentle on the driving source. The output impedance, like the inverting case, is greatly reduced by feedback. Using the same feedback factor, beta equals R sub G divided by open parenthesis R sub G plus R sub F close parenthesis. The closed-loop output resistance becomes R sub out approximately 1 divided by open parenthesis a sub all times beta close parenthesis. Because beta is typically smaller than 0.5, the output resistance is even lower than in the inverting topology, often a few milliohms for modern CMOS op-amps. Consequently, the non-inverting stage can drive low impedance loads without much voltage drop. Real op-amps have a finite gain bandwidth product, GBW. The open-loop gain a sub-OL drops at -20 decibels per decade after a single dominant pole, so the product a sub-OL times F remains roughly constant. When we close a loop with gain of V, the closed-loop bandwidth FC is approximately GBW divided by the absolute value of a V. For example, a 1 MHz GBW device set to a gain of 10 in the inverting mode will have a -3 decibel bandwidth near 100 kHz. The same rule holds for the non-inverting case. Slew rate SR is the maximum rate the output can change, expressed in volts per microsecond. If the input is a sinusoid of amplitude V sub p at frequency f, the required rate is 2 pi fv sub p. The circuit will distort if 2 pi fv sub p exceeds SR. Thus, a 10-volt peak, 100 kHz sine needs SR greater than or equal to 2 pi times 100 kHz times 10, approximately 6.3 volts per microsecond. Exceeding this causes the output to look triangular, slew rate limiting, and the effective bandwidth shrinks. Both GBW and S are set practical limits on how fast and how large a signal the amplifier can reproduce. Several non-idealities spoil the perfect gain formula. A. Resistor tolerances. If RF equals 100 kilohms plus or minus 1% and Rin equals 10 kilohms plus or minus 1%, the worst-case gain deviation is about plus or minus 2%, sum of relative errors. B. Finite open-loop gain a sub-OL, the closed-loop gain becomes a V equals negative RF over Rin divided by open parenthesis 1 plus 1 over a sub-OL beta close parenthesis, where beta equals Rin divided by open parenthesis Rin plus RF close parenthesis. With a sub-OL equals 100 kilohms and a gain of -10, the error is only 0.01%, but grows as a sub-OL falls with frequency. C. Input offset voltage V sub-OS. The op-amp adds a small DC voltage to the differential input, which after being multiplied by the closed-loop gain appears as an output offset V off equals V sub-OS times open parenthesis 1 plus RF over RG close parenthesis for non-inverting, or V off equals V sub-OS times open parenthesis 1 plus RF over R in close parenthesis for inverting. For a 1 millivolt offset and a gain of 10, the output shifts by 10 millivolts, which may be significant in precision circuits. Temperature coefficients of the resistors and bias currents also contribute small errors. Designers mitigate these by using matched resistor networks, laser-trimmed op-amps, and guard techniques. Explanation: exam style practice. A close parentheses determine resistor values for a specified gain dash. Suppose a teacher asks for an inverting amplifier with a gain of -47 using a standard 1 kilo ohm resistor series. Choose Rin equals 1 kilo ohm, then RF equals 47 kilo ohms. Nearest E96 value 47.5 kilo ohms gives gain -47.5. Verify the gain formula. B close parentheses. Compute output voltage for a given input signal dash with the above circuit. Apply a sinusoidal input Vin of T equals 20 millivolts times sine of open parenthesis 2 pi times 10 kilohertz times T close parenthesis. The expected output is V out of T equals -47 times 20 millivolts times sine of ellipsis equals -0.94 volts times sine of ellipsis. Check that the magnitude does not exceed the supply rails ±5 volts, so no clipping occurs. C close parentheses. Identify saturation and clipping conditions dash using a non-inverting amplifier with gain 15, powered by plus minus 12 volts rails, and an input that can swing up to plus minus 0.9 volts. The ideal output would be plus minus 13.5 volts, which exceeds the positive rail. Therefore, the op-amp saturates at about plus 11.5 volts considering a 0.5 volt headroom. The result is a clipped waveform. The positive peaks flatten at plus 11.5 volts, while the negative peaks remain at minus 13.5 volts, clipped at minus 11.5 volts. The exam may ask, at what input amplitude does clipping begin? Answer: when absolute V in times open parenthesis 1 plus RF over RG close parenthesis equals V supply minus V headroom. For a 12-volt supply and 0.5 volt headroom, that is absolute V in equals open parenthesis 12 minus 0.5 close parenthesis divided by 15 approximately 0.77 volts.